In this section, we'll look at using the timers to automatically handle all of the timing associated with the A to D converter, the reference settling, as well as the sampling time. We'll also cover some needed interrupt handling code. Each counter compare register can be used in different timer modes to generate interrupt flags. Here in the continuous mode, you can see that using timer B, here's timer B, counter compare register 1, compare register 0 are being used to generate interrupts at each different point. You can generate independent PWM frequencies with different duty cycles automatically when you're in continuous mode using CCR 0 and CCR 1 or 2 and 3 and 4, however many it takes to do the pattern that you're interested in. Timer B, counter register 1, compare 0, and being used to generate interrupts at different point. We're going to optimize in the next lab the timer triggering for the A to D converter. Right now, for the power optimization, we're currently having the timer delay 2 seconds for the software trigger. That's 2 seconds between sampling. The optimization here is that the timer will do that 2-second delay, then it will enable the reference for the timer B interrupt flag rollover. Then it will trigger the ADC12 sample and conversion using the timer B CCR1 output. This SHP bit down here selects whether the sample time is set by the timer B CCR1 output or this equation here. This is the one that we're going to use. At the speed that we're running, we're going to get about 40 microseconds there. So the time between timer B interrupt flag and timer B CCR1 has to be about 75 microseconds for the 2.0 volt reference to stabilize. Let's take a look at that a little closer. Like I mentioned earlier, there's only so many interrupts that can go into the CPU. There is the timer B0 vector here. That comes off of the timer B CCR 0, but any of the other CCRs, CCR 1, 2, all the way through 6, and the timer B interrupt flag, if you're going to recognize those all go through the interrupt vector register and come into the CPU as timer B1 vector. That means we have to have a handler that's going to see which one of these actually went off. The handler is pretty simple, whether you do it in assembly or whether you do it in C. Basically, you have to look at the values inside this timer B0 interrupt vector register right here. So if you take a look in there, the contents of that can be a 2, a 4, an A, and so on, depending on which one of the counter compare registers went off. In this case, here's case 2, where CCR1 went off, case 4 is CCR2, and case 10 is the timer B interrupt flag register there. We also need to set up the ADC12 interrupt control. The power optimization on the ADC12, currently we're doing polling for the interrupt flag from ADC12 MEM1. That's after the voltage has been sampled. The optimization is that we're going to enable that interrupt flag so that it actually generates an interrupt to wake up the CPU only to handle the conversion data. So the AD12 interrupt enable bits enable the interrupt request on a write to the respective MEMX register. So ADC12 MEM1 has the end of sequence set, so the interrupt gets requested after the sequence of temperature and VCC over 2 conversion is complete. Reading that MEMX register will clear the respective interrupt flag, so we're going to have to read that ADC12 MEM1. The handler for the ADC12 interrupt flag 1, we're going to have, if you look at this, there's a series of different cases where there's no interrupt pending, ADC12 overflow, conversion time overflow, ADC12 MEM0, that's when the temperature gets read, and ADC12 MEM1, that's 8. So at case 8, we're going to want to disable the reference and the ADC, any further sampling, read out the MEM0 and MEM1, exit active back to main so that the conversion can take place. That's the simple interrupt handler there for ADC12. The flow for the Lab 5 code, same kind of main here with all the basic initializations. Then we enter the sleep mode LPM3. Now we wait for the 2-second delay to go off. That will be the timer overflow interrupt service routine over here. When the timer overflow goes off, it will turn on the internal reference and enable the ADC12 conversion to start. Once that's started, it exits. We then wait for the ADC12 MEM1 interrupt service routine, the interrupt from ADC12 MEM1 to go off. That will kick off this interrupt service routine. It then disables any further conversions, disables the internal 2-volt reference, reads out ADC12 MEM0 and MEM1, and then exits active from LPM3 to go back to right here, where the temperature and VCC can be processed and output through the USB. We go right back to sleep and start all over again. The Lab 5 power numbers look best of all. The CPU is asleep the majority of the time right here. In fact, it's awake so little we really can't even see it. 2.1 microamps in low power mode 3. So the CPU now is no longer active like in Lab 4. It was active during the entire time when the internal reference is on. So when the reference is settling and the sampling is taking place, the CPU is not on at all. The ADC12 interrupt service routine wakes up the CPU for a very short time at the end here during the entry and exit to the interrupt service routines, when it disables the reference, when it stores the ADC12 MEM0 and MEM1, the temperature and VCC values, and then it wakes active on exit to do the processing and goes right back to sleep. So that's a very, very short period right here. So you can see we've again gotten the majority of the time down to 2.1 microamps, but now where our maximum here is somewhere around 252 microamps. This is about as far as we can go to minimize the power consumption for this application. Lab 5 implements the same application as Lab 4 did, but the CPU usage has been fully optimized through the use of timers for all of the delay needs. Lab 5 is a fully optimized ADC12 routine. We're going to use the ADC12 interrupts to signify the end of the conversion. The timers are automatically handling the delay time, the trigger time, the settling time, everything that's possible to be saved we're doing in the timers. So although we're not going to see the current drop that much compared to what it did before, this is pretty much as fully optimized as you can get for this kind of application. Following along in the workbook, let's take a look at step 1. I'll close this editor window, go to Lab 5, and set it as the active project. I can minimize what's going on in Lab 4. Here's Lab 5 right here. I'd like you to make sure that lab5.c is excluded from the build and that the solution is included in the build. So you can open up the lab5 solution.c for editing. Taking a look at step 3 in the workbook, go ahead and step through you can see that we're putting timer B into continuous mode. Go ahead and take a look on your screen. There's the HAL board init. There's the HAL timer init right here that's shown in the book. And if you page down, you can see how it's initializing ADC12 to work in the program. The timer ISR enables the reference and conversion. The ADC12 ISR disables any further conversions, disables the references to conserve powers, reads the value, and then turns everything back on so that you can exit the interrupt service routine. So in step 4, go ahead and power your board by turning on the multimeter. Click the debug to download the program to the board. It's downloading to the board. We'll click Run, as shown in step 5. And then again, we want to make sure that the board is actually sending information up to us. So I'll clear the information from the terminal here, the terminal window. And the board is sending information up to us right now. So you should see the scrolling temperature down below in your terminal window. Again, it's at 103. I'm going to heat my finger up with some friction and then put it on the top of the chip. There's 107, 109, 109. I'll take my finger off and you can see the temperature drop. So we know we're getting real information up from the processor. So for the current measurement in step 8, we want to disconnect the JTAG cable from the board. Click the disconnect button in the terminal window and then observe the current consumption on the meter. Now at this point, if you look in step 10, again, because of the timer delay and the meter's inability to quickly move around for us, you can see we're jumping back down to 1.4 or so, somewhere in there. That's 1.4 microamps. And then the amount of current it's drawing in the meantime, according to our diagram, is jumping up to 252 microamps, but that's hard to see on the meter. So I'm going to write down 1.4. That's where we are for the majority of the time. So in this application, the CPU is not active either during the delay time or during the reference settling or the sampling. The CPU is allowed to wake up for a very short period of time to enter and exit the interrupt service routine and store the results. That's it. So we're in step 11. I can reach over and turn off and disconnect our meter from the experimenter's board. I'll reconnect JP1, switch back to the FET, disconnect the cable from the board. In Code Composer Studio, I'll click Terminate All, and we're done with Lab 5.